Okay, AP Chem, today we're going to try to understand a concept which was related to gases that can be the most confusing. So solids, liquids, and gases are our three common states of matter. Now, solids and liquids behave more similarly to each other, whereas gases have a lot of unique properties that are much different than solids and liquids. So you might have seen a variable before that is the volume of a gas. So if you are at standard temperature and pressure, the volume of a gas, doesn't matter what kind of gas you have, is 22.4 liters per mole. Now let's look at the ideal gas law. And we know that liters is related to volume and moles is related to N. So let's rearrange so we have liters on the top and moles on the bottom. So right now, volume is on the top, and so is moles. So let's leave volume on the top and get moles on the bottom. So we're just rearranging the equation, and PV over N is equal to RT. Now we need liters on the top, which is volume, moles on the bottom, which is N. We're good. Now let's just get rid of P on the top. We'll divide each side by P. And now we have volume over N equals RT over P. So let's read this rearranged equation and tell us what it says to us. The volume of a particular gas, when you have 22.4 liters in 1 mole, means that the temperature and the pressure, so when the temperature and the pressure are the same for any gas, the volume is the same for the number of moles. So this 22.4 is related to standard temperature and pressure. The standard temperature is 273 K. The standard pressure is 1 atmosphere. This is where the ideal gas law constant came from. So I'm going to rearrange one more time and remind you where the ideal gas law came from, because if you rearrange this all to solve for R is equal to PV over NT. At standard conditions, this is always going to equal the same value for the constant, which is the ideal gas law constant. So pressure is 1 atmosphere. Volume is 22.4 liters per 1 mole at 273 K. So right now we're deriving the ideal gas law constant. And if you put this in your calculator, 22.4 times 1 divided by 273 times 1, you will get the ideal gas law constant, which is 0.08206 liters atmospheres per moles K. That's just deriving the ideal gas law constant. So let's go back up to our 22.4 liters. At standard temperature and pressure at STP, 1 mole of gas will have a volume of 22.4 liters. We're almost never at 22.4 liters, so I'm super hesitant to even bring up this variable. But the reality is, it doesn't matter if we're at standard temperature and pressure. It doesn't matter what temperature and pressure we have. The volume of any gas will be the same. So let's say you're not at standard temperature and pressure, which is 273 K and 1 atmosphere. Let's say you're at 298 K and 1.10 atmosphere. It doesn't matter what gas you have, it's still going to have the same volume. So we could list off any types of gases. Let's make a list of our super common gases, like CO2 is a super common gas. CH4, which is methane, is a super common gas. SO2, sulfur dioxide, is a super common gas. NO2, NH3, so on and so forth. And then we have our diatomic gases, which are elemental gases that come in pairs. Those also have the same volume if they have the same temperature and pressure. So N2, O2, H2, Cl2, F2. So on and so forth. So you could list off any number of gases, also our noble gases, right? We could list those off. Any gas, doesn't matter. If these gases are at the same conditions, in order to be in the same room, they would have to be at the same conditions. In order to be in the same container, they have to be at the same conditions. All of these gases would have the same volume. It doesn't necessarily have to be standard temperature and pressure, and the volume doesn't necessarily have to be 22.4 liters. But you can know that if gases are in the same conditions or the same container, then they will have the same volume regardless of the identity of the gas. So this is not by any stretch of the imagination a comprehensive list of gases. Here is just a list of gases that if they're at the same temperature and pressure, they will have the same volume. Okay, so remember that we're investigating the ideal gas law, which is PV equals nRT. I'm just going to rearrange and solve for R, which is our ideal gas law constant. So that will be PV over NT. What we mean by the fact that this is a constant is this never changes. That means that if one variable is manipulated or changed, another variable or more than one is going to respond in order to counteract that change. So we can always calculate what's going to happen with the other constants, or the other variables, because they're all going to equal a constant at all times. So remember, if there's variables that are multiplied, they're inversely related, which means pressure and volume are multiplied by each other. That means if pressure goes up, volume goes down. Or if pressure goes down, volume goes up. That's what we mean by a relationship. And an inverse relationship means as one goes up, the other goes down. Now, these variables that are divided by each other, for example, volume and temperature. If the temperature of a gas goes up, the volume of a gas goes up. We know that logically. If you heat a container of gas, it will expand if it's allowed to. For example, a balloon. Same thing, if you increase the number of moles of gas in a particular container, the volume will go up. Pressure, same thing. Pressure and temperature are directly related. As one goes up, the other goes up. So this is a relationship that tells us a lot about gases, and they're always going to equal a constant. So if temperature and pressure are the same for any gases, we can tell some things that will be the same. The volume will be the same. Let's say that our conditions are the same. Let's stick with standard temperature and pressure, and you can Google standard temperature and pressure. This is something that is set and that we don't have to calculate or anything like that. So Standard temperature and pressure is called STP, and that is a pressure of 1 atmosphere and a temperature of 273. Okay, so if we're at STP, let's say we've got a bunch of gases at STP. If we have a bunch of gases, let's just list a sample example of some containers that have gases in them. We're going to say that we have 3 containers. One has CO2, one has O2, one has neon. If the pressure for all of them is the same, then, and the temperature is the same, then the volume is all going to be the same. And also the number of moles is going to be the same for all of these. So the things that are going to be the same, if the volume of the container is the same, if you have identical containers and they are in the same room together, so the pressure is the same and they have the same temperature, then you know you're going to have the same number of moles. So there's certain things that we can say are the same. So in this particular example, the things that are the same are the pressure, the volume, number of moles, and the temperature. But let's talk about the things that are different, because not every thing is going to be the same here. There's some things that are going to be different. So what is definitely different is the molar mass. Neon and oxygen and carbon dioxide have different molar masses that you would look on the periodic table of the elements to come up with. 32 for oxygen. Carbon dioxide is 32 plus 12.01 or 44.01. And these are in grams per mole. So we definitely know that something that's different about these gases is their molar mass. The other thing that's different, because the molar mass is different, now let's remind ourselves of our molar mass Kitty equation. Our molar mass Kitty equation states that a good kitty puts dirt on top of their pee, or dirt over their pee. So if we look at this, obviously R is the same. It's always the same. If the temperature and the pressure are same, but the molar mass is different, then something else has to be different. And that is the case, is that if pressure and temperature and obviously R are the same, but molar mass is different, then density also has to be different. So this is the reason, one of the good reasons why this molar mass Kitty, or the density formula, becomes important, is it allows us to figure out the identity of the gas based on the things that are different. And for different gases, couple things that are different are their molar mass and the density. So let's clarify one other thing. Do we know what temperature measures? Temperature does not measure heat. Temperature is a measure of the average kinetic energy in a sample. So that means that if you are at the same temperature, it doesn't matter what substance you have the same average kinetic energy. That does not mean that each molecule has the same average kinetic energy. Doesn't mean that every molecule has exactly the same kinetic energy. There's going to be some that move faster and some that move slower, but the average kinetic energy in the sample will be the same if the temperature is the same. So for those of you who have gone through physics already, or probably from middle school, you'll remember that the kinetic energy is equal to 1/2 mv squared. So we know that the temperature in this particular example is the same. Therefore, the kinetic energy is the same for all the different individual gases that I have. Well, the mass is not the same because it has a different molar mass. We have 1 mole of each of these gases in this example. So if we have 1 mole of each of these gases, the mass of this particular sample is going to be different. Of these particular samples is going to be different. So if kinetic energy is the same because temperature is the same, that means that something else has to be different besides the mass. So in this case, it is the velocity. So kinetic energy equals 1/2 mv squared. This is lowercase v, not to be confused with uppercase V, which is volume. So therefore, another thing that is different in this particular example, because the mass is different, it's also the velocity. And let's look at this equation. The larger the molecule is, remember, in order for this to be constant over here, these two are multiplied by each other. A larger mass is going to have a smaller velocity in order to remain a constant relationship. So they're multiplied by each other. They're inversely related. The larger the mass, the slower the velocity. So big molecules move slower with the same energy. So it's the same concept as if you think of a giant freight train. The bigger a freight train is, the more mass it is carrying from point A to point B, the slower it will be moving. So objects with a larger mass will have a smaller velocity in order to have the same kinetic energy as a small mass will have a large velocity. So that's like a teeter-totter. So you can think of a really slow-moving train. You know, if it hits you, it's going to have a lot of kinetic energy and it's going to cause a lot of damage, whereas a small object would have to be moving very fast in order to have that same amount of energy. So when we talk about gases, if we have an equation or a problem that states to us we have neon, oxygen, and carbon dioxide in 22.4 liter containers and we have 1 mole of them, we know that it's going to have the same pressure and the same temperature. The things that are going to be the same in this particular type of example are P, V, N, and T. The things that will be different will be the molar mass, the density, and the velocity of the sample. So you will need to know, conceptually wise, what are the things that are the same and what are the things that are different.